why this talk as a journey from art to part? Because obviously the title doesn't reveal that it has a lot to do with Python in itself. The explanation for this is simply that Python has managed to become the major scripting language in all the computer graphics packages I work with, which is a fantastic thing, because how many weird Visual Basic like dialects can you get into? What kind of other scripting languages do you want to dig in? Some manufacturers fiddled with Java-like dialects. So to become proficient in scripting in those languages, and we come to the point why you want to do that to begin with, was arduous to begin with in the past. Now in the last, I'd say 5 years, Python has managed to squeeze out every other scripting language and become the major scripting language in all computer graphics packages. And now let's see where that has an influence. We'll do a little journey. I will show you a couple of projects I am involved in. Those are portfolio projects. I pretty much designed all the items, or modeled the items, or machined the items. I'll introduce the pipeline. What is a pipeline? Pipeline is basically the flow from the conception of a product to the produced result, and what is involved, software, mechanical instruments, everything builds this pipeline from A to Z. Then which programs are involved in the pipeline, because my description of the pipeline will be rather generic. All the programs we're going to see in detail in a minute. Now, the generic functionality of those programs, of course, allows already the manufacturing of parts, which we'll see in the beginning. But certain products have benefits compared to other products, and you would like to take from one product to the other. Often products, software products, are proprietary, which means that the vendors take great care and pride in the fact that you cannot open file A in program B. That's where Python comes in really handy, because being that a common scripting language enables you to build your own data transport between those applications. Because as we will see, the core functionality of all those applications is very similar. So once, I haven't had the time yet, but you could basically build a wrapper, abstract in that wrapper to the functions of those computer graphics packages, and then work on an even more abstract layer on the tasks you want to automate or accomplish. Then what is used to output that stuff? That's for the technically interested. I'll show a few machines, what they do, and how they achieve the manufacturing process. And that will conclude our little trip. And in the custom functions, I can show a few applications of Python I created for my own benefit. And so if somebody has questions, just interrupt me. This is not a streamlined affair. If somebody has an interest in something, then the slideshow will be available upon request through my, just send me an email. I'm more than happy to forward you the slideshow as PDF file. In the slide are quite a few links for products involved. So it might be useful for somebody who's in this more machinery side. Okay, without further ado, let's continue. We have 23 slides, which are rather quickly skipped, and then I have a couple of live demonstrations. So it probably take like 30 minutes to 50 minutes to get through it. The more questions you have, the more I appreciate. So let's see. So this is just a computer graphics. Thanks for not being able to show it in HDMI. It's actually a nice image. It looks a little bit like less than it is. It's a fractal structure, which is computer rendered. more than happy to show it on my real screen later. The graphics are falling a little bit apart. This is more a mechanical modeling I did. I made a sculpture out of it. It's called Unity. It's several segments interlinking in the same way. I hope you can visualize that on the screen. Has anybody a problem with the resolution of the screen, or is it bearable? Is it okay? Good. Then that's a woodworking project which I made using CNC machines. CNC machines are, for people who are not familiar with the term, computer numeric controlled machines. It's nothing else as a term for machines where a cutting tool is moved according to computer instructions. So everybody knows what a plotter is. Imagine a plotter with a Dremel drill attached to it, where you can lift and drop the Dremel drill. And then you basically use instructions similar to the ones you would send to a plotter, and you move the cutting tool around. Now they're machines of different sophistication in their amount of moves they can perform, and this is one of the results of it. Was rather tricky. It's sort of a trial to get one of those 4D cubes visualized. We go to industrial projects. This is a rather large boot. The company I'm working for currently produces items for retail venues, large shopping malls, large playgrounds for children, interactive playgrounds. And I'm responsible for the technical aspect of all this. We have now interactive play pieces where you walk up to, say, interact with you, they start to vibrate, or they start to talk to you. We have all sorts of sensor technology in there, which we have developed in-house. There's a lot of embedded electronics involved with custom microprocessor, single board computers and stuff like that. It's a lot of fun, especially the motion detectors. They're all microwave-based, radar-based, similar to those microwave detectors on top of automatic doors. You have this little black box, you walk towards the door, and then all of a sudden the door opens. We use the same technology. It's basically radar because we built the detectors into the pieces so they're not visible. So you cannot use infrared or anything else to detect motion. So we use radar. So we literally microwave small kids on our playgrounds. Of course, with safe frequencies and doses, but it's always fun to say it that way. So this is a slide. You can actually walk up in the heel of the big boot and then slide down. And yes, it's made for a playground in Texas. So then this is one of my favorites. It's a cartoony car, a little bit like Roger Rabbit, that car. The way it's produced is we use a 3D CNC router, which is pretty much like that plotter example. I said we put a big foam block in, and then a cutting tool basically skims the surface and carves the shape of this car into it. You know, when you take a look at an orthographic view, which means straight view, you could not reach the inside of the car or the... And we only have a movement of about 10 inches. So what I do is, when we design an item like this, we think about how can we slice this model in the computer and then position the pieces that when the machine is done carving the item, we can reorient them, glue them together, and we end up with this car. That is then coated with a hard plastic. It's a very interesting machinery. It's big barrels of basically a super glue that's heated up to 160 degrees, shot out of a gun, like a spray gun, and covers the styrofoam core of this model in seconds, and the stuff sets in about 3-4 seconds. It's like it's scary. So if you're in the spray booth with the operator of that gun and you tick him off, you won't be able to run out. He gets you located in place quicker than you can turn around. So Then what we do is we sand this roughly, and we upholster it with a EVA foam, which is like neoprene, to make it soft for kids. So if somebody runs towards a car chasing somebody else and he stumbles and falls against it, it's only a boink and not a crash and ambulances and 911, so that doesn't happen. Then we put a layer of a sprayable rubber on top of the EVA because this neoprene is not very durable. You could take your fingernails and take that foam apart. So we put a harder rubber on top, which is then airbrushed and clear coated. And after all those steps, we're all very tired, and we're fueled by the giggles and the laughs of the kids we can observe once in a while when we install those pieces. So this is like a cute car, but we have very wild pieces we produce, and it's worth a complex process. Then from large, you can also go to small. You can see the size of the pin. That is a carving I made for a client for a bathroom vanity. That strip of wood is an inlay. It was gilded, which means that you apply gold foil to it with a little bit of glue under it, and looks really, really nice when it's done. So it doesn't matter if you make large things or small things. It's all the same technology, the same programming. Those are just for the people who probably never saw something like this. This is a range of cutting tools. They all look rather vicious, but all those cutting tools, as you can see, have different shapes. Sometimes you want to carve a V-slot. You all have seen signage, which has those the old wood shop or pub signs, which have those V-shaped engravings. You can do those with cutters which have those V-shaped heads. Then if you carve things like that car, you would like to take a cutter which has a round tip, because the round tip eliminates traces of the hard edge of a square tip when it passes over round features. So there are different selections. I don't want to bore you with that. You can see you have almost microscopic cutters, which is pretty much used for that last sample I showed you with the wood. And then you have large cutters, which are often used just to plane something or to rough out shapes very quickly. Often this carving is not used just to produce a finished product. It's often used to give you a 70% product, hand-shaped, for example. So you can determine with the roughness of your design how much machine time do you want to have versus manual labor, and where are the benefits back and forth. And so that's the tree of those tools we use compared to 3D printers, where the modeling is, you will see it later, the modeling is the same. If you want to see 3D print it, if you want to use a 3D router, if you want to use a robot, that was German. If you want to use a robot, it really, till almost the last moment of all this art-to-part workflow, till the last moment where you decide which machine you want to use, there is a difference. You prepare your art, your parts for the production process. 3D printers versus all the other technologies, there's one major difference. 3D printers are additive. So they take a plastic, which they heat up, or a photo substrate, and they build up material, which then represents your product in the end. It's like, for people who are not familiar with 3D printers, it's basically a very simple machine. Instead of having a cutter on your plotter, you have a hot glue gun. And that hot glue gun basically lays down hot glue and layers and layers and layers it up, and you can imagine you can get some shape out of it. Where all this technology takes a big block of wood or foam and then subtracts what you don't want. So those are the two worlds, and there is no other difference. Then this is a sample of a project. Here it's a computer rendering of a shape of a Christmas ornament. It's a large Christmas ornament, like 5 feet diameter for a mall. The goal is to have a crystal ice thing hanging, which will be lit from the inside. So here you see this is one of those 3D routers. The cutter is at the end of this tip. It's invisible because there is at least the attempt of a dust collection which surrounds this cutter. You see a lot of debris, and the cutter is basically cutting the shape out of a block of plastic, actually, suitable for this process. Then here is the final product. Then a little bit hard to see right now because the resolution is a little low. There's a shiny surface on this, and what happened is we take transparent sheets, like 4x8 foot transparent sheets of polystyrene. It's like your polystyrene cups you get from Party Central for plastic champagne glasses. It's the same material, basically. And we heat that up. It's like a big panini press. That sheet is suspended from above with elements. And when it reaches a certain temperature and it's quite limp and puffy, the part here is lifted towards it. The sheet is set down, is applied, and this sheet is sucked to the shape of this. It is cooled down quickly with pressured air, and then extracted. And here you can see this is a sheet I'm talking about. It's leaning against a 4-foot-high wall, and the rest is a shop. So you have an idea. So this is a clear piece that is then manually cut out. 2 of those are fit to each other, and there you go. You have your big ornament. So why am I showing you this? The reason for this is if you have ideas for your own home decoration or you want to build furniture, there is no reason why you should using a 3D program to design your own things, because this is easily done by a lot of fabricators, even around here in the tri-state area. You give them that file and you say, well, you might not want to have this 5-foot ornament in your home, but if you want to build like furnitures for your own apartment, you want to have you have a studio, you need a built-in. You say, I don't want to waste all this space because IKEA only has furniture which almost fit, and you have like inches around space. You can design your own stuff, and for a little more than IKEA, have it made somewhere, because the machinery makes it so cheap to make custom stuff. Good place to go is those people who make kitchens. They also do other stuff. They just don't have it on their advertisings. So here's another project that was for a high school graduation. Somebody gave me art. It's like for a yellow brick road kind of themed graduation party, and there were Clockwork Gears which should be glued upon a flat surface, which otherwise has this print on it. And here again, I designed the gears right off the drawing. We might see in a minute how to quickly do this. Here you see now the cutter exposed. The spindle is turns with about 18,000 RPM, rotations per minute, and it cuts into a foam block, very hard foam, which is made for sign makers. And it cuts pieces out, and at the end of the day, when it's done, well, end of the day is indicating a long time. It actually takes an hour to cut a whole 4x8 sheet with all this detail. Then it can be taken out, glued up on a surface, and painted. So it's a fairly quick process to go from this drawing to the part, about a couple of hours till they're finished, which is, if you have to cut those with a jigsaw, yeah, you better take a week for this. So I don't have an endless amount of those presentations. Here's another one, a very quick one. We produce Easter sets. Easter sets are setups where in shopping malls where you can go and have pictures taken with a big Easter bunny. It's those moments where you get all the hilarious pictures on the internet of kids screaming and yelling and in sheer panic and terror. So we make those sets. We also make Christmas sets, and the latest one is Halloween. We never made a Halloween set, which is actually now really cool, because what we did is big stand-ups with cartoony witches and devils and steins, and you can stand behind them and take a picture. You look through, put your head through, and there are like lots of stand-ups in the set, so you can walk around, take your own pictures. So I'm looking forward to get some pictures from that. So this is just a sample. Those are flowers cut out of MDF. MDF is a material, it's a man-made wood, basically pressed sawdust, medium density fiberboard. It's horrible material. When you cut it, it's a very, very fine dust. And we have to be very careful with the dust collection there because it's not very good for your health as an operator. Once it's painted, who cares? But so now this is a computer rendering, and I think it looks pretty close to the final product. We have AstroTurf, we wrap this in, and then powder coat the stems and paint the flowers, put them on top, deliver them, and get a check for that. So that is another quick project. Then here is, we're almost done. Here is a so-called hot wire cutter. It's a little bit difficult to see, but there is a wire down here which is electrically heated. And in a two-dimensional way, who has ever built a model aircraft? Nobody. You can use a hot wire to cut in styrofoam with like two handles. You give a little tension to that, and you can cut shapes. The same principle here, just computer controlled again. Only two-dimensional. So if you use Adobe Illustrator, we all know what Adobe Illustrator does. So if you lay out some curves, you can give that directly to this cutter, and you would get it cut two-dimensional into a material any thickness because you lack the third dimension. So I devised, it's one of those moments where you say, okay, you get the request, we need to make a balloon or an Easter egg, and you say, yeah, no problem. You know, it's like programmer, you get, so I need a sort for this. Yeah, sort. You stop thinking after sort, and then you see the data, and you're like, what did I just get myself into? And this was one of those moments. I don't want to bore you with the details, but it took me a little moment to be able to cut those shapes, which are compound curves, with a two-dimensional foam cutter. So the way I did it is I used two views to get to that shape, and it yields with two cuts you can get this shape. And it was a great moment when I found that out that it actually worked. So I kept my job a little bit longer. So then to make things worse, projects like this always get worse. This is the top of the balloon. The machine can only cut 50 inches. The balloon, as you can see here, is about 8 feet tall. So to make it more complicated, I had to also figure out how I can do that in segments without losing the shape. So that was one of those moments where when you think long enough spatially, it's like with programming, you get into the zone. You almost have a feeling how you're going to do it. So yeah, lucky again. So this is coated again and airbrushed, and it's a nice balloon. You see a couple of clouds which attach to the sides. The rest is a slide. So the little guys have a lot of fun with this. And this introduces this hot wire cutter. So we already have quite a few machines we looked at. Then this is a good sample for the art we get into the shop. Some artist comes up with the idea, we want to have a little boat with a little guy in there. And this is a fantastic artist, by the way, because they provided a few views for us. And this is the final result. We also made a little firehouse light boat. That again comes out of the same workflow than all the other stuff you've seen before. Here is another sample, now with a little detail. Up there is a cat example for the watermelon. It kind of looks like a blood orange or so. It's supposed to be a watermelon. There are actually seeds in there, I promise. So this is a crawl through which has a 2-foot diameter so kids can go through without getting stuck. In the age group we usually build playgrounds for, we haven't seen kids with more of a girth than 2 feet, knock on wood. So we have orange. It's about 3 feet tall. You can climb on the orange and sit on the orange. It's for a playground in the south. But you can see the models we make. Then we see we determine if all the thickness of the materials is sufficient for stability. I do some analysis how difficult it would be to push it over or so, and then we produce a piece. So now this is it. The part of the boring project is over. Now we're getting a little bit closer to Python any minute. The pipeline from art to part is we receive drawings or image files, Illustrator files, anything just from a design point of view. We start 3D modeling because why don't we go directly to production? Because sometimes 3D modeling also reveals inherent problems with the design. Hence the problem art file unusable. Then we got to go back to the artist and say, hey, you got to change something. The best example for this I have is Escher. We all know Escher with the waterfall and the impossible geometry he has. We do get art like this sometimes, where people come up with this idea, we make the structure and please build it. And then I say, nope, we don't. So then there is a program which generates, and that's where we nail down which machine we are using, the machine toolpath. Toolpath is a descriptive word for where does my cutter go, or where does my hot wire fly. This is determined there. After that, this code will be loaded into the machinery and then tried out. Then we see if the product's okay, because sometimes your drawing is too coarse, your toolpath is too coarse, or God knows what, the tool is too fast, it breaks. We set the machine on fire, can happen. And but if everything's smooth, we just fulfill the order, we start churning it out, and then ship it and collect money for it. So we'll take a look at this in detail in a second. And where Python comes in play is pretty much in here, in the 3D modeling phase, because the rest is not very exciting, actually, in the entire product flow. Here is a list of the programs involved. Everybody has a preference for programs. I saw a very funny picture on the internet yesterday, not that there are many, but it was about religious fanatism. And we had the 4 standard religions, and then somebody was smart and put Apple was like, Apple people are way more fanatical than anybody else. To that person who made this bar chart, I can only say, you haven't talked to computer graphics people. So they just are a complete different breed. There are preferences for whatever reasons. So where does this selection come from? This selection comes from about 10 years of dealing with computer graphics programs and their manufacturers. Because there is an honorable mentioning of Adobe and Autodesk, both big players. And why do I only give them Adobe honorable mentioning? Adobe switching to the subscription model they have right now, and the fact if you don't pay the ransom every month, you can't even access your data anymore, is, in my opinion, not a legit business model. So do I pay my share right now? Yes, but if there's a chance, I would jump to another boat. Autodesk is, I'm a little bit torn about this. There is a product called Maya, and there's another one, 3ds Max, both fantastic programs. But Autodesk has this proprietary over it. You can't open their files with anything. You can't exchange data. And where there is exchange data, there are libraries built by Autodesk which are once in a while politically modified. I stay out of that realm. So, but those are fantastic programs. And if there's a reason to use them, there is no functional reason. It's just you have to be very careful if you bet your business on using those programs, because you have to look contractually what you get yourself into, because also maintenance is not cheap for those systems. So which brings me to the next point. How much does this stuff cost? This is a little bit too expensive. Well, I'm careful because I own the licenses myself, but it might be expensive for an amateur. who just wants to have a couple of nice pictures or so. But those are affordable for people who can write them off. If you're a 3-man company, you can have seats for everybody, and you're still making money using those. Yes?
Are there open interfaces that makes this stuff?
Yes.
So
absolutely.
I mean, if you understand the data, like shapes of the data, you could like
absolutely.
make anything fit.
So if I understand your question right, is am I able to, in the whole process, to throw in my own programming to generate geometry or to even generate the toolpath myself?
Right, like
absolutely.
Other than only like having access to the hardware that manufactures these different things, you know, is there a gatekeeper?
No, there is all those machines are controlled by. The nice thing is manufacturing is way more streamlined than all the software stuff. If you talk to manufacturing people, there are electrical standards, there are machining standards, there are languages for machines, and it's all open because all those players have learned over the years that you're going to die if you're. There's a sample. There is a robotic language which died together with a Japanese company which was keeping it proprietary, while another one was taken the whole realm in storm because it was used by all the big players, auto manufacturers, and. But just to expand, very, very little time on this. I just want to see, of course, my phone I have a stopwatch running theoretically. Yeah, we're still good. To go from the machinery back to the software, of course, the closer you go to the software, which generates the modeling software, the more diffuse this becomes. But the good thing is, the closer you get to the machinery, the more open and defined it is. So having that said, all those machines understand the same code. And it's a very simple code. It is, for example, M4 and M5 are the two commands that switch the spindle on and off. F is for the feed speed, determines how fast your cutter is slicing through the material. Maybe it breaks or not. Then G is a go command, and it accepts 3 parameters, X, Y, and Z, or an angular command. So having that said, you can write already a little program with a text editor to cut a square out. That's it. It's as easy as that.
Have you ever heard, like you mentioned Illustrator?
Yes.
To create curves.
Yeah.
Have you heard of Inkscape?
Yeah, you can use that too.
Did you use Inkscape?
Absolutely. Yeah.
Sure.
I'm staying away clearly from programs like SketchUp, Inkscape, because I felt that if I recommend them, people just jump on them because they're open software, free software. And then to a certain degree, if you try to get into it commercially, I don't want to say you wasted your time, but you played with something which is way inferior to what this offers you. I'm talking about the difference between Notepad and WinWord. Yeah.
Would you say the same thing applies comparing, for instance, Blender to Cinema 4D?
Blender and Cinema 4D. Blender, to expand on it, probably nobody else knows what Blender is. Blender is an open software which is very comparable to Cinema 4D or Maya. It's written by a group of people. I dared to go so far and say loosely connected people. So a lot of modules within Blender are not necessarily from the UI from the user interface point of view, it's hard to navigate at times. You can use Blender. You will have less support. It is a little bit more basic. It's like OpenOffice versus Microsoft Office. So you do get your form letter done, and if you swear enough, you even get a mass mailing out of OpenOffice. But Windows, you can do the same thing, but a little bit in mind. Where are we price-wise? We're with Cinema 4D. We have a $600, $700 piece of software. Rhino 3D, $900 new. You can find it cheaper on the internet. ZBrush, this is a nice-to-have piece of software, but just mention it so you can go to the webpage and see what it does. That's about 400, 500. Vectric software is a whole toolkit of sign maker software and so on. I don't want to go too much into Vectric now. I just put it on because it's a very nice product. Then a couple of utilities. C4D to Rhino. This is a Python written program, which I want to show what it does. It just gaps those programs. Moa 3D is Rhino 3D is built on an open NURBS, on an open modeling kernel, and Rhino 3D is from a company called McNeil, and Moa 3D is a recent product from the guy who left McNeil to build his own. Then Rhino CAM is CAM stands for Computer Aided Manufacturing, and this is a product which generates the toolpath, basically analyzes geometry and builds the instructions for the machines. And then we got some robotics software, which is interesting to look at. Ooh, robotics sounds complicated. Our company I work for is not a car manufacturer, so we dismissed robotics for a long time, where actually robotics are really cool because you, with an immense degree of freedom, analog to a human hand, you can actually also undercut things with your cutting tool. You can reach much further than just a stupid 3D plotter. So it's good for us, but it's expensive. So last time I looked at it like 5-6 years ago, it's like $100,000, $200,000. And you have something called ROI, return of investment. If you don't have that, it's just a tool. It's just a hobby. You know, we can't afford a hobby. So recently I was at a manufacturing fair here in the Javits Center. Yay to the Javits Center for being 10 minutes away from where I live. So, and I talked to the robot guys again, you know, like the little guy who runs around the candy machine and says, if I would have a quarter, I would buy one. And a new system came down to $70,000, which is like shocking. And now if you do what the gentleman in the back already has led up to, you use your own bronze to get yourself a little bit closer to a solution. There's in real life always, when you know how to do it, you don't have to pay somebody to do it, and then you save a lot of money. So if you buy a used robot, and there's a lot of companies who are offering used robots, you can get one for $20,000. Then you use like the HAL from Thibault Schwarz, a fellow from Switzerland, together with Rhino 3D. That's $900. That's $1,500 if it all comes together. You have a full-blown robotics package where you can model a product and you can carve any sculpture, statue right out of the solid without even looking at it. It's a little bit tricky because you enter another realm of complexity where you have to hold the robot's hand a little bit. You have to analyze what it does. You can't just let it run because there are situations where mathematically there are points it reaches where to achieve the next move, there are infinite possibilities. And then it's not necessarily that the software uses a smartest move. It could go like, turn itself around to reach a different point instead of just continuing on this. So, but it's all software driven, it's all visual. So you see your model robot do what the big one later will do. And if it's sufficient, then you just let it run, and for $20,000, $30,000, you have a Robocop standing in your shop carving for you. Yeah, it's very impressive. So now those are the software products, Cinema 4D and Rhino. Why do I have two modeling programs? Those are two modeling programs. Why do I have those? First of all, they both support Python as scripting language. Then the other thing is there are two worlds in computer modeling. One world describes the shapes by mathematical formula. So, and the other world is describing the geometry in shape of like a fence, like a chicken fence with little faces, faceted. So they're not really compatible, so it's very beneficial to have one of each. Cinema 4D also allows you to render your products in a way that they're very desirable for clients to look like eye candy aspect. Rhino 3D is more a technical product. Cinema 4D allows you computer animation, rendering, and modeling in the polygon world. And now I just keep it easy there because I'm getting too much into the modeling aspect. Then here we have the custom functions, and I'm going to load the products in a second. Something like descriptions for those products. So if you're inclined, you can have a quick look at what it means. Then there are a couple of third-party links which are really cool to look at regarding further tutorials in that realm. The API functions, and I did that very, very roughly. The typical API functions across all those computer graphics packages are the math libraries, which allow you to translate objects, modify your geometry, graphical user interface, because as we will see in a second, Cinema 4D, for example, allows you like really easy to define a slider in the user interface, or entry fields, or file path names. And then you can utilize that information with a one-liner from Python to get your data into your Python code. So in case you want to open a file, or you have some geometry you want to scale, and you want to do that interactively, the GUI part of those API functions would be the place to look. Bitmaps and textures, not necessarily interesting, except you want to render something real nice for a client. But then you can put bitmaps like if it's supposed to be sand. I get the sign from the back. How many minutes do we have? 10 more minutes. So textures, when you render something, you can see the surface better. File handling, of course, getting data in and out. And geometry, how to deal with your geometry, saving it, rotating it, generating geometry. So now, quickly, to a couple of examples, which I made. I hope I have to get my screen back. Let's see how I can share this. Let me see if I can get the set up. Just switched into this shared mode. I don't want that. Good. Okay, so here we go. I think the resolution, yeah, it's okay. This is how the Rhino modeling software looks like. You have different views for the same thing. I'm going to speed up a little bit at this point. You can create geometry like a wall here in the middle. Represented with design. Here again, you can see this ball is actually a square, but it's represented by a mathematical formula. So it's bent by the formula parameters, and it has a seam. So it's basically a plane which is wrapped around. It looks like a ball. So what I do in this program, I'll keep this short. I skip the eye candy a little bit. When we do machining, I have a 4-foot by 8-foot board of material, and I want, this is like Illustrator, I want to have a few parts on it. And one of the things is when I generate parts, I have like maybe a few hundred on there. So I say, this is a door, for example. I give this part a name so I can identify it later. And this is a panel simply. So now I have people on the factory floor who require a printout of this plan. Once the stuff's cut, they know what's on the machine and what they have to use for what. So a big deal is now to prepare this. I don't want to go through 200 different items and type in PyGotham door, for example, and take a text element and fiddle that to everything. So if I print this, it looks nice. So what I did is, it's one of my first Python programs in Rhino. I created this button here. It's a nice, friendly green button, and it resets the Python engine. So now I can select objects to mark, and what happens is we become. They get a text point, it's called text point, attached to it, which is a copy from this name. So all my parts will have this attached. So if this seems to be a little bit too big, I can just select all of those, makes the font smaller so it can actually print, because you can see if I have a couple of hundred of those, then it would be too big. Now I can print this. This seems to be a simple thing, but I can tell you I have a few of those little helpers, and that is a godsend to be able to do this in Python. And all it takes is a script where I select the objects. This is the function I use to select the objects, and I loop through the list. Then I decide which kind of object I have attached. And then down here, I create the so-called text dots with this. So I don't have to go in and get used to some other Visual Basic dialect in this language just to do this. So this is my very quick sample in Rhino. I could save this file in Rhino format, and I'm just skipping through it so you get a little bit more of the benefit here. This is Cinema 4D. It has pretty much the same setup. I have a little bit more functionality here regarding timelines for animation, but the viewport is pretty much the same. Here I prepared a very small sample. How could you use CSV data, for example? You generate it in Python, or you get it from big data or something. Where is my... So I have a Python code I prepared, which allows me to take user data. This is what I talked about earlier. Right out of a field, I can design interactive data is just to play with. And if I fire this, the Python reads this file, it is capitals of the world, and basically generates text objects in Cinema 4D, spreads them around according to latitude and longitude, something which will take a long time if you would have to model that manually. And here we go, it already read it in. It's, again, just a couple of lines. When you're familiar with the API in Cinema 4D, you can wax this together in an hour. It took me a week. It's the first time I was looking for CSV file import. And you can see it's the resolution. It's and all those elements here are automatically generated by Python as a plugin. So the other plugin I can't show you now because of time constraints. I can tell you what it does is I can actually save files in Rhino and we import them conversion. Proportion. All sorts of things. The cinema for the course. So that was only possible because you have Python in both sorts of languages. Now, if there's somebody who is interested in more information, you got my email address. I am more than happy if somebody wants to take a step further to assist. I am living in Manhattan. I have a small shop in East Orange with CNC machinery. So if you're interested and inspired, I'm also working on a project which enables me to apply constraints in a computer model, which means imagine I design a shelf, and now I want to make the shelf out of 1-inch thick wood plates instead of 3/4-inch wood plates. The constraints I would define would enable me to do this, and everything would automatically shrink and grow into the right proportion to this. So it involves a solver. It's a little bit of artificial intelligence in there. So now you're informed about the steps how to make stuff using 3D programs. And thank you for your attendance. I have a picture. No, we actually. Only to. So this is a industrial robot. The machine on the left is an industrial robot, and there's a friend of mine who has this system, and we just ordered the same system for the company I work for. So,
Thank you.
you're welcome.